Students, in this lecture we will study the applications of linear algebra to graph theory. First of all, we will study about the graph, which is directed graph. What is the concept of directed graph? If you see here in this figure, there is a graph which is directed from each vertex to other vertex because of this arrow. These p's, p1, p2, p3, p4 and p5 are called the vertices of this graph, and we see here that there is an edge from p2 to p3. This is directed towards p3, so this edge, this link is from p2 to p3, not from p3 to p2. There is difference between p2 to p3 and p3 to p2. This arrow shows that this edge is directed from p2 to p3. So this is one directed edge of this graph. Similarly, p1 is directed to p2, so this edge, this directed edge, is from p1 to p2, not from p2 to p1. Similarly, this edge is from p1 to p5. This edge is from p5 to p2, and this edge is from the both sides, from p2 to p4 and from p4 to p2. Similarly, this edge is from p5 to p3, and this edge is from p3 to p4. That edge is from p4 to p5. So this kind of graph is a directed graph, and this whole story is from this figure, that for this figure the set of vertices is all those pi's, p1, p2, p3, p4 and p5. These are the vertices for this graph, and there are directed edges. The first edge is from p1 to p2. So from p1 to p2, this edge can be written in ordered pair form p1 p2. p1, remember that, p1 p2, not p2 p1. p1 p2 means this is the edge from p1 to p2, and this is written as p1 to p2. Similarly, this edge is from p1 to p5. So from p1 to p5 can be written as p1 comma p5 in ordered pair, and in arrow form this can be written as from p1 to p5. Similarly, this edge is from p2 to p3, which can be written as in ordered pair form p2 p3, and in arrow form from p2 to p3. And all those edges, this is from p2 to p4. So from p2 to p4 can be written as p2 p4, and in this fashion from p2 to p4. Similarly, from p3, from p2 to p4, p2 to p3, and from p3 to p4, that is the edge, which can be written in ordered pair form just like that, and in arrow form just like that. Similarly, from P4 to P2 can be written as in this fashion, and in arrow form in this fashion. And from P4 to P5 can be written in this fashion, and from P5 to P2 can be written in this fashion. So the finite collection of ordered pairs is, these are all ordered pairs, 1 2 3 4 5 6 7 8. So this is the finite collection of ordered pairs from here. As we see here that there is an edge from P2 to P4, and again from P4 to P2, so these two combinedly can be written in this form. This arrow is one-sided and that arrow is two-sided. It means that there is an edge from P2 to P4 and from P4 to P2. That is the definition of directed graph. That directed graph is a finite set of elements, which are called vertices. Finite set of elements, these elements which are called vertices, together with finite collection of ordered pairs, which are called directed edges. This is one directed edge from P1 to P2. This is second directed edge from P1 to P5, and this is third directed edge from P2 to P3, and so on. Edges Pi, Pj of distinct elements of this set. We see here that each element of this set is an ordered pair notation. That is the first ordered pair, that is the second and third and fourth. No ordered pair is repeated here. If we see here that there is P2 P4 and that is P4 P2, so there is difference between P2 P4 and P4 P2. This is from P2 to P4 edge, and that is from P4 to P2 edge. So no ordered pair is repeated here. So is repeated. That is the definition of directed graph. That directed graph is finite set of elements which is called vertices, together with the finite set of the collection of ordered pairs, such that no ordered pair is repeated. So that's how we define directed graph. Now the second topic is vertex matrix of a directed graph. A square matrix M, capital M, whose entries are in the form Mij, M11, M12, M13, and so on, so on. So a square matrix whose entries are Mij and whose order is n by n is vertex matrix. This matrix is vertex matrix if this entry Mij is equal to 1 whenever there is an edge between Pi and Pj. So if this is M11, so there must be an edge, directed edge from P1 to P1. If that is 1 2, so there must be a directed edge from P1 to P2. Anyways, if there is an edge between two vertices, so the entry will be 1, and if there is no edge between two vertices, so the entry will be 0. So it means that the vertex matrix only contains ones and zeros. For example, that is a directed graph, because directions are given to us, arrows are given to us, and there are 4 vertices, P1, P2, P3 and P4, and we want to make a vertex matrix for this directed graph. So first of all, we will make a table, we can say that, and write these vertices P1, P2, P3 and P4, and the first row, V means vertices, so write vertices in row form here, and write these vertices in column form here. So this entry will denote that whether there is an edge between P1 and P1 or not. So we see here that there is no edge, there is no loop. We can say that you studied this thing in discrete mathematics, that what is a loop. So there is no loop, there is no edge between P1 and P1. So between P1 and P1 there is no edge, so this entry will be equal to 0. And whether there is an edge from P1 to P2 or not. So you will see here, from P1 to P2 there is an edge, so that's why P1 P2 is 1. Similarly, whether there is an edge from P1 to P3, so P1 is here and P3 is there, there is no edge between P1 and P3, so that's why this P1 P3 is 0. Similarly, edge from P1 to P4 is missing, so that's why there is 0 here in P1 to P4. And then just look at this P2, whether there is an edge between directed edge from P2 to P1. So we see here that there is no edge from P2 to P1. This edge is from P1 to P2, and from P2 to P1 there is no edge, so that's why P2 to P1 is 0. Similarly, P2 to P2 is 0 because there is no loop here, so this is 0. And P2 to P3 is, there is an edge from P2 to P3. Just look at that, from P2 to P3 is an edge, so that is 1. And from P1 to P4 there is no edge, from P2 to P4 there is no edge, so that's why this is 0. Similarly, you can repeat this for these two vertices from P3 to P1. P3 to P1 there is no edge, so that is 0. From P3 to P2 there is an edge, you see here, from P3 to P2 there is an edge, so that is 1. Similarly, from P3 to P3 there is no edge, and from P3 to P4 there is an edge. From P3 to P4 this edge exists, so that's why here is 1. And similarly, from P4 to P1 no edge is there, so that is 0. From P4 to P2 no edge is there, so that is 0. From P4 to P3 there is no edge, so that is 0. And from P4 to P4 there is no edge. So we see here that this is a kind of a matrix this matrix is called the vertex matrix, and this is denoted by capital M. So M for this directed graph is this one. Similarly, if you look at this directed graph, there are 5 vertices. So make a table with 5 vertices in our first row and 5 vertices in the first column, and examine the edges from P1 to P1, which is missing, so that is 0. Edge from P1 to P2 exists, from P1 to P2 exists, so that is 1. From P1 to P3, from P1 to P3 there is no edge, so that's why that is 0. And similarly from P1 to P4 there is no edge. We see here that from P1 to P4 there is no edge, so that's why this is 0. And from P1 to P5, we see here that from P1 to P5 there is an edge, so that's why this is 1. Similarly, repeat this process from P2 to P1, there is no edge. There is no edge from P2 to P1, so that's why this is 0. And from P2 to P2 there is no edge. From P2 to P3 there is an edge. From P2 to P3 this is exists, so that's why this is 1. From P2 to P4 there is an edge, and from P2 to P5 there is no edge, and similarly all this table. So this matrix thus obtained is called the vertex matrix for this graph. So that's how we make a vertex matrix from the given directed graph. That is one question, which is actually your first question of this section. That is question number 1, section 11.7. Construct the vertex matrix for each of the directed graphs illustrated in the accompanying figure. You are given a figure here. That is the first figure. You need to draw a vertex matrix for this figure, similarly for this figure, and for this third figure. That is your question number 1. That is about vertex matrix. Whenever a graph is given to you, directed graph is given to you, and you need to construct the vertex matrix. What are the properties of vertex matrix? We see here that in vertex matrix all the entries are either 0 or 1. So all entries are either 0 or 1. And if you look at this main diagonal, the main diagonal of vertex matrix is 0. So main diagonal, the entries in the main diagonal are 0. So these two are the properties of vertex matrix. Here's a theorem that how could we find the number of r-step connections from one edge to another edge, from one vertex to another vertex. Let's say M be a vertex matrix of a directed graph. You are given a vertex matrix which is obtained from a directed graph, and let's say Mij to the power r, Mij to the power r be the ijth element of m power r. This m power r, what does it mean? You need to calculate m square, m cube, and so on. So that is the entry which is obtained by multiplying m 2 times, 3 times, and so on. Then this entry Mij to the power r is equal to the number of r step connections, number of are step connections from pi to pj, pi to pj. That is a theorem. To understand the statement of this theorem, let us consider an example. For example, there are 4 cities, P1, P2, P3 and P4. 4 cities are there, and among these cities a small airline services exist, and among these cities this graph shows the route from one city towards second city. That is the direction, that from city 1 you can move to city 2, and from city 2 you can move towards city 1 and city 3. You cannot move from city 1 to city 4 because there is no directed edge from P2 to P4. Similarly, you can move from city 3 to city 1 as well as to city 4, and similarly you can move from city 4 to city 3 and city 2 and so on. So that is the vertex matrix for this directed graph. I think you can understand this matrix, that how could we find this matrix from this graph. This is the connection between P1 and P1, so that is 0. That is the edge between P1 and P2. That is the edge between P1 and P3, and that is the edge between P1 and P4. Now for P2, so from P2 to P1 there is an edge. From P2 to P2 is missing. From P2 to P3 is edge, and from P2 to P4 edge is missing. There is no directed edge. Similarly, that is P3. So from P3 to P1 there is an edge. P3 to P1 there is an edge. P3 to P2 directed edge is missing. P3 to P3 edge is missing. P3 to P4 directed edge exists. P3 to P4 and similarly. So that is the vertex matrix for this directed graph. We need to find the connections from city 4 to city 3. What does it mean? That in how many ways we can move from city 4 to city 3. For example, we can move from city 4 to city 3 directly. We can move from city 4 to city 3, then from city 3 to city 4, and then from city 4 to city 3. That is second route. Similarly, we can move from city 4 to city 2, and then from city 2 to city 3, and again from 3 to 4. So how could we move from city 4 to city 3 actually? So we need to find the connections. So for that purpose we need to find the powers of this given matrix. Find m square. How could we find m square? M into n. So m into m. How could we multiply these two matrices? First row with first column to get this answer, then first row with second column to get this answer, first row with third column to get this answer, and first row with fourth column to get this answer, and similarly second row with first and second, third and fourth column to get those answers. So multiply these two matrices to get this matrix, which is m square. Now again we need to find m cube. How could we find m cube? That is m into m square. M is this one, and m square is this obtained matrix. multiply these two. Whenever you multiply these two, you will get this matrix. Now just look at this connection. We need to find the connection from CT4 to CT3. So it means that we will concentrate M43, P4 P3. So we will concentrate M4 M3. So from matrix M, from this original matrix, M4 3 is the entry in the fourth column, fourth row and third column of M. So fourth row and third column of M, this is M43. So from matrix M, M43 is 1. So there is one step connection from, there is one step connection from P4 to P3. It means that whenever you go from CT4 to CT3, you need just one edge to move from CT4 to CT3, which is observed from here that this one edge exists. Similarly, from M square, we should concentrate M43 square. M43 of M square is fourth row and third column. This is 1. So M43 square is 1. So it means that there is one two-step connection from P4 to P3. One two-step connection. It means that taking 2 steps to reach from P4 to P3, and that is practically, if you see here, you can move from P4 to P2 and then from P2 to P3. So there is one two-step connection from P4 to P3. Similarly, from M cube, you need to find M43 cube. M43 cube, that is M43 cube, fourth row and third column. So M43 cube is 3. It means that there are three step connections from P4 to P3. Whenever you need to approach P3 from P4, so there are 3 ways. And 3 steps you can move from P4 to P3. If you look at here, you can move from P4 to P3, that is 1 step. Then from P3 to P4, that is second step. And then again from P4 to P3. So one 3-step connection is this one. Similarly, you can move from P4 to P2, that is 1 step, and again from P2 to P1, that is second step, and then from P1 to P3 is the third step. So that is second 3-step connection from P4 to P3. And the third, because we have 3 3-step connections, that is 1 3-step connection, and this is second 3-step connection, and then you can move from P4 to P3 in the third way. So practically, if you look at this verification from the figure, that is the given figure, and 1-step connection from P4 to P3 is only one. Only one. We have studied in the previous slide. So there is only one step connection, and that is from P4 to P3. Similarly, there is only one two-step connection from P4 to P3. Only one two-step connection. That taking two steps to reach from P4 to P3, there is only one. That is given to be. You can move from P4 to P2. Just look at that. P4 to P2, and then from P2 to P3. So this is actually two steps. This is one step, and that is two steps connection from P4 to P3, which is only one. Similarly, we have proved that there are three step connections from P4 to P3. How many three-step connections are there from P4 to P3? There are three-step connections. Just look at this. 1, 2, and 3. That is one three-step connection. 1, 2, and 3. That is second three-step connection to reach from P4 to P3. And this is the third three-step connection to reach from P4 to P3. Namely, you should move from P4 to P3. P4 to P3, again from P3 to P4, P3 to P4, and then again from P4 to P3. So that is one three-step connection. Similarly, you can move from P4 to P2, P4 to P2, then from P2 to P1, and then from P1 to P3. So that is the second three-step connection from P4 to P2, then from P2 to P1, and then from P1 to P3. That is the second three-step connection. And that is the third three-step connection. You should move from P4 to P3, move from P4 to P3, then from P3 to P1, P3 to P1, and then again from P1 to P3. So that is the third three-step connection. No three-step connection exists other than these three-step connections. So how could we obtain step connections? We need to take the powers of the given vertex matrix m square, m cube, m4. Take the powers and then concentrate the given connection, that which connection we need to obtain, and find those connections from the given vertex matrix and from the powers of the vertex matrices. The last topic of this lecture is clique. That is not click but clique. What is a clique? That is actually the subset of a directed graph. If we take the subset of a directed graph, what does it mean? A directed graph is made of some certain vertices P1, P2, P3, P4 and so on. If we take some vertices from there, so that will be the subset of that directed graph. So the subset of a directed graph is called a clique if it satisfies the following three conditions. The first condition is the subset contains at least 3 vertices. Remember that for a clique, if you take the subset of a directed graph, so those vertices, the number of those vertices must be at least 3. We should take at least 3 vertices. At least means kam se kam. So at least 3 vertices. So more than 3 is possible, 4, 5, 6 and so on, but 2 and 1 are not possible. So clique contains at least 3 vertices. The second one is, for each pair of vertices, if we take the edge, so that edge must be between pi and pj and from pj to pi. So the edge from pi to pj and then from pj to pi is true for each pair, for every pair. And thirdly, that subset which is taken from the directed graph, that subset is as large as possible. What does it mean? That if we take 3 vertices, so there will be not there will be no existing fourth vertex to make a subset which is clique. What does it mean? The subset is as large as possible. That is, it means that it is not possible to add another vertex to the subset and still satisfy this second condition. Anyways, these 3 conditions must be satisfied by a subset to be a clique. There are notes for simple directed graphs. Simple directed graphs are those graphs which contains less number of vertices. For simple directed graphs, cliques can be found by inspection. We can see, we should look at the graph and we can identify the clique directly when the graph is simple. The graph is simple, that there are not too many vertices and that directed graph. For large directed graphs, it means that if there are many vertices of a graph, then how could we find the cliques for that large directed graphs? We define a matrix S. We define a matrix S whose entries are Sij as follows. Those entries, this entry Sij will be equal to 1 if there is an edge between, there is an edge from pi to pj and then from pj to pi. So whenever these two edges exist, then the entry will be equal to 1, and for all other possibilities the entry is 0. So we define this kind of matrix. From the vertex matrix, S can be obtained. Vertex matrix is denoted by M from the previous slides, and this matrix S is different from that vertex matrix. So this S can be obtained from the given vertex matrix as Sij, the entries of this matrix will be 1 whenever the entries in the vertex matrix Mij and Mji, whenever these two are equal to 1, then Sij will be taken 1, and whenever these entries are not 1, then the entry Sij of this matrix will be equal to 0. And the second note is, how could we identify the cliques for large directed graphs? So there are 2 steps. First of all, we need to find S cube, the cube of this S matrix. First of all, find S, by this criteria, and then find the cube of that S by multiplying S 3 times, and observe the main diagonal SII. Observe the main diagonal of this S cube. Secondly, the vertex PI of S cube. The vertex PI of S cube will belong to some clique for which the diagonal entry SII is not 0. If S11 is not 0, then P1 will belong to some clique. If S22 is not 0, then P2 will belong to some clique. If S33 is not 0, then P3 of S cube will belong to some clique. So that is the criteria to identify the cliques. That first of all, find this matrix S, and whenever you find this matrix S by this method, or that if you are given a vertex matrix, then you can find S directly by this criteria, and then identify the cliques by these two criterions to find the cube of this matrix S, and then look at the main diagonal where the entry is not 0, then corresponding to that entry, that vertex will belong to some clique. And remember that the clique contains at least 3 vertices, not less than 3 vertices. More than 3 are acceptable, but less than 3 are not acceptable. So that is the criteria to identify, to find the clique of a given directed graph. Let us take an example that how could we find clique. Example is, find clique or cliques, if any, for directed graph having vertex matrix M is equal to this one. We see here that this matrix has 4 rows and 4 columns, so it means that there are 4 vertices of that directed graph. So 4 vertices are there, and 4 vertices are there. We need to find the cliques for this kind of directed graph. In order to find cliques, we need to find the matrix S. So how could we find S matrix? Just look at this M. This entry is M12. I mean, this is in the first row and in the second column. So that is M12. This is M12, and below this, and this diagonal, reverse diagonal, this entry is M21. So M12 and M21 are equal to 1, so it means that S12 will be equal to 1. S11 is 0 because A11 is 0, M11 is 0, so that is 1. Similarly, this is this entry is M13. Now search about M31. What is M31 entry? Third row, first column. So third row, first column is this one. So you see here that M13 is 1 and M31 is 0. They are not equal, so that's why this entry will be 0 and S. Similarly, if you look at this one is in the first row and fourth column. So this is M14. M14. Now try to search M41, fourth row, first column. Just look at this. These are two consecutive rows, so 1 and 1 are near to each other. That is the third one, so search about the third row. That is fourth column, so search about the fourth row. This one is in the fourth column, so search in the fourth row opposite to this one. Anyways, so this one and this one with that entry, this one with that entry. This is M14 and this is M41. So these two are equal, so this entry will be equal to 1 and S. Similarly, this is 1, so that is M. This is M21. This is M21 and that is M12. These are same, so this entry will be equal to 1. And just look at this entry. This is 0, so that will be equal to 0 because this is not 1. Search for ones. Okay, this entry is 1, so this entry is in the second row and second column, so that is second row and third column. So this is M23. So try to search M32. This is M32. These two are same, 1, so this entry and S will be equal to 1. Similarly here this is 0, so that will be automatically 0. Search for only ones. Just look at this one. So this entry is in the third row and third column, third row and second column, so that is M32. So try to search M23. M23 is this entry, second row and third column. These two are 1, so this entry and S will be equal to 1. Similarly this entry will be equal to 1. It means that if there is 1 and opposite to it there is 1, so these two will be equal to 1. And the third column, if there is 1, so look at in the opposite to this and the third row, if these are 1, so this entry will be equal to 1, but unfortunately these two are not equal. Similarly you should match this one with the entry in the fourth column. If these two are 1s, so these two will be 1s and S. Similarly this entry with that entry, if these are 1s, so these will be automatically 1, and similarly these two are 1, so these two will be automatically 1. So that is actually S matrix. We need to find the powers of this S. Power means S cube. So for S cube, first of all we should find S square. S square is Sn to S, so multiply this S 2 times, rows into columns, to get this matrix, and then find S cube by multiplying S square with S. This is S square and that is S, multiplying these two matrices to get this matrix. And now we need to observe the main diagonal of S cube, for clique. So the main diagonal of S cube is 0, so it means that there is no clique for this directed graph whose vertex matrix is given to us here. So there is no clique for this kind of graph. This second example will more explain the idea of clique. We are given the vertex matrix for a directed graph. So first of all, for clique, find the S matrix. This is S matrix. These two are ones, so automatically these two will be ones. This with that are not one, so this entry will be 0. This with that are 1, so this entry will be 1. This with that one is 1. Now this is 1 automatically, that is 0. 0 will be 0. Okay, just search for ones. This is second row, third column, fourth column, second row, fourth column. So this entry will be matched with this entry. These are ones, so automatically these will be ones. And similarly this one will be matched with this one. This is A3 4, so A4 3 is this one. This is A4, this is A3 4, A3 4. So search for A4 3. This is A4 3, fourth row and third column. So these two are simply that the first of this diagonal, the semi diagonal, the first will be matched, will be the last one, and in between will be matched. Similarly this reverse diagonal, this first will be matched with the last one, and this one will be matched with that one, and that will be left alone. Similarly that will be matched with the last one, second will be matched with the second last one. Similarly this third will be matched with the last one, and this will be left alone. This will be matched with that one, and so on. So this will be matched with that one. So using all those criteria, that criteria to find S, this is S matrix. Now for clique, find the square of find the cube of this S by finding S square first, by multiplying this S 2 times to get this matrix S square, and for S cube multiply this S square with S to get S cube. And now from the main diagonal of this S cube, this is the main diagonal of this S cube, this element is M11 cube because of this cube. This is M11 cube, M22 cube, M33 cube, M44 cube, M55 cube. So a main diagonal M11 cube is 2, and so on and so on. So, and we see that M11 cube, M22 cube, and M44 cube are non-zero. These are not 0, whatever the numbers are, but not 0. So it means that from M11 we should take P1, for M22 we should take P2, and M44 we should take P4. So P1, P2, P4 belongs to some clique, because these entries are not 0. So this is P1, concerning with P1, P2, P4. So P1, P2, P4 belong to some clique, but we know that clique has at least 3 elements. Clique has at least 3 elements, and these are 3 elements. So there is only one clique, namely P1, P2 and P4. If these vertices were 4, then we should combinedly take those 4 along with 3, and there will exist more than 2 cliques maybe. Anyways, in this example there are 3 vertices which belong to some clique, and clique has at least 3 elements, so there is only one clique. namely P1, P2 and P4. So that's all about clique, and that is the last topic of this lecture.